Hello, friends. Welcome to Enlightning. It's a special nighttime, at least North American nighttime edition. And we're here with Sunil, who's visiting us from Australia, and is going to teach us about Kepler. Hello, Sunil. Will you tell us about yourself, please?
Hey Whitney, how are you?
I'm
I'm Sunil. Sorry, I'm Sunil. I work in the sustainable computing space. I work for Red Hat and currently focused on Kepler and its ecosystem. And I'm here to explain what Kepler is to you all.
excellent. Oh, I'm so excited. So, first, before we dig into what Kepler is,
Mm,
tell me, please, what the world was like before Kepler. What problems were happening that caused Kepler to get created?
well, the biggest drive, I'd say, is to focus on sustainable computing.
Uh huh.
And uh, when we speak about sustainable computing, we need to measure to improve our sustainability. So as software goes more into cloud
Uh
and
huh.
consume resources that you can't even measure, there is a greater need for some tool that's able to uh, understand uh, the exact consumption of a process or a pod in Kubernetes world.
Uh huh.
And we needed a tool that is able to do that. There are many that is able to um, look at a power meter, for instance, RAPL or ACPI, and then able to report that at a level that aggregates all process running on a machine. But if we want to go deeper and see what each tenant on a cloud is consuming,
Yeah.
uh,
So the problem, we have software is in the cloud and it's consuming cloud resources, but we don't
yeah,
have very much visibility or zero
granularity.
visibility.
Yeah,
Uh,
so we need granularity into what my process is consuming or my workload is consuming with
okay.
respect to someone else. Uh,
Okay.
Say,
So,
for instance,
uh-huh.
a bank may be running 1,000 services,
Mm-hmm.
and we want to measure what each service is consuming, the power that it consumes, the energy that it consumes, and how it can be optimized as well.
Okay.
And
Um,
mhm,
I would coming at this for completely from the outside, I
yeah,
would think I would make an assumption, maybe, or at least think that the more memory and compute I'm consuming, therefore the more energy I'm consuming. Is that not true? Why do we need
uh,
to? Yeah.
yeah, it is true. But how do you then quantify? So, how do you convert that into the watts that you consume? Right? Um, so that's where Kepler comes in to actually keep a tab on every process that gets scheduled onto a machine and measure how much time it's consuming in the CPU, and then translate that into the power that it is utilizing.
So I'm going to ask just silly questions, but
Mhm.
why do I need to know the wattage? Why isn't it enough for me to be like the more memory and CPU, the more energy? So therefore, I'm going to try to minimize my CPU, which, by the way, in memory, which will also save me money.
Yeah, you can. That's one way to go about doing it.
Uh huh.
However, the uh, let's say you're running a machine and
Uh huh.
uh, it consumes some power by default.
Uh huh.
So now let's take that to one more step, which is that you're deploying your workload onto a public cloud
Uh huh.
where a machine would be shared across multiple tenants.
Uh huh.
Uh, and then you've got to account for the base consumption across all the tenants as well. So just measuring how much power your workload is consuming or your hypervisor or your virtual machine is consuming is not sufficient because there is an underlying issue of base power which needs to be divided across all the users. So let's say there are two clients running on the same machine, and even if none of the clients are running their workload, the machine itself running consumes some energy. Let's say 200 watts is what it consumes at a base
Uh-huh.
level. And then you deploy a tenant's workload onto that, or let's
Mm-hmm.
say two tenants workload onto that, each consuming, say, 10% of the available CPU.
Mm-hmm.
What you really want uh, to count is the total consumption divided across both clients equally. So
Okay.
that the base power, that is 200 watts, we said, is equally accounted for both the tenants. And for that, just measuring how much the CPU consumed if by one is not sufficient to give you how much power. So when you want to report, that's my carbon footprint, uh, you've got to somehow translate the CPU time to the power that you're using. Uh,
So
mm,
if these are hosts,
mm,
and each host takes 200 watts to run, regardless of
yeah,
what's running on
mm,
top, right?
yeah, yeah,
And then this machine, it has 3 workloads on it. And
yeah,
what? So this is a workload.
mm.
That's a. I'll just put this. And then our base. Did you say how much did you say a base might have?
Let's say that because there are three, uh, let's put 210, 70 each, or 300, for instance.
Okay,
Uh,
300 watt. What's the unit?
yeah, watts, yeah,
Watts.
yeah,
Okay.
yeah,
And then this one is 300 watts,
yeah,
but it's only running 2 workloads.
yeah,
And then the workloads themselves have some sort of calculation. We'll say each one is
exactly.
100.
Yeah. And the terminology we use is idle and dynamic,
Uh, idle, as the host is idle and the workloads is dynamic.
correct?
So we can say a workload running over here where it's not optimized is using 250 altogether, 250 watts. Where a
That's
single
right.
workload running over here is only using 200 watts.
Yeah.
So I understand, but I also still think that, like, in general you're using less energy, but what isn't that intuitive that you want to, I guess they call this bin packing, that you want to maximize what your machine is running just to save yourself, so you're
Yeah.
maximizing the machine use.
Yeah,
So
exactly. Yes.
so
And
yeah.
yeah, yeah. I'll let you finish.
Oh, so why do we need Kepler to tell us that it's more efficient to put more workloads on one host?
So Kepler doesn't tell you which host to put the workload on. It only tells
Uh-huh.
you that the workloads on machine A, for instance, is consuming 100 idle per process and 100
Okay.
dynamic per process. Now, that's so Kepler is more like an observability tool that is able to look at the process running on the machines and
Mm-hmm.
then give you an idea of what is the power consumed by each of the process running on the machine. And the and Kepler looks at idle and dynamic, which is not, I think, reported by any other tool prior to Kepler.
Uh, idle. IDL. Idle measurement.
Yeah,
Idle measurement. is this 300, and then this 100 is dynamic.
Yep.
Measurement. So what is the definition of Kepler? Let's get that onto the board.
Yeah, Kepler, I would define as a Prometheus exporter that
Okay.
exposes power-related metrics at various levels.
Cool. It's power related Kubernetes? Is it Kubernetes specific or no?
It is not Kubernetes specific. It
Okay.
is so you can run Kepler on your machine, run Kepler against in a Kubernetes environment. It is cloud aware in the sense that it understands the concept of Kubernetes, containers, pods, virtual machines. So when I say it exposes power-related metrics at various levels, the levels can be a process,
Okay.
and many processes can run in a container, so at a container level.
Okay.
Then we have many containers running in a virtual machine, so at a virtual machine level, so
Okay.
which is VM, and then
Host
the
machine.
entirety of the node. So that's at the node level. So I just need to know what my node is consuming. So that's the node level.
Okay.
Oh, we missed the pod.
Exposes power related. Okay, what did I miss?
This one more, which is pod. Many containers
Okay.
make up a pod in Kubernetes world. So uh,
I was thinking about that, but then also I thought it's not Kubernetes specific. So maybe okay.
it
Pod
understands
be
Kubernetes.
okay. Cloud aware.
Yeah.
Excellent. So I'm a company. I want to save money. I want to run my workloads efficiently.
Mhm.
How is Kepler informing my actions? Maybe maybe I do care about. I mean, I think everyone, in all seriousness, should absolutely care about being green.
Mhm.
Um, is there a case where being green is not the same as being efficient and cost effective?
Um, it could be, but um, one way which Kepler allows uh, you to be green and efficient and cost effective
Uh huh.
is to, let's say you have Kubernetes and Kubernetes has scheduler.
Uh huh.
It's pretty easy to write a scheduler which looks at the values exposed through Kepler
Uh huh.
and schedule your workload based on whatever
Ooh.
logic you want to choose. So that could be so you can go more sustainable, or
Yeah.
let's say there are some part of the cluster that runs on green energy, solar or whatever, uh,
Mm-hmm.
and choose that first before pick another workload. So we have a project called Peaks, which is able to uh, which is a scheduler for Kubernetes that looks at Kepler metrics and schedules workload accordingly. So that's an example where you can be both green and you can pick how you like to optimize your workload. Kepler has no say in how you do that. It only exposes these values for you to pick where the workload should be.
Mm.
So when
That was a lot of words. You can use Kepler metrics to make a Kubernetes schedule that schedules workloads that maximize energy efficiency.
Yeah, so you can maximize to whatever you need. So it could be energy efficiency. It could be that I'm maximizing or lowering the carbon footprint because one metric that usually companies want to produce is that my AI workload is only consuming this much, or that it has zero carbon footprint, for instance. So uh, what you call efficient is dependent on what you want to achieve.
Energy, okay. Am I still on that? Okay. Carbon footprint. So, I know you've kind of told me how it works, but can we talk more about how it works?
Yeah. So one thing that we have left out, what Kepler provides, is that in public cloud, where you don't have, where you are not running a bare metal, you're using a VM, a virtual machine. You don't have access to power meters, so you can't read how much power is being consumed, because that's one way to actually spy on other workloads on the same machine. So that's not exposed. What Kepler provides is a machine learning model that tries to closely mimic what the underlying power meter would produce given the CPU usage. So we're building models that mimic the power curve of a CPU.
So Kepler has an
a machine
LLM or
learning model.
an
Yeah, I
that
wouldn't
makes
call it
more
a.
sense. Okay.
Yeah. If you don't
Like
need
that's just
LLMs for, yeah, we
has
need
a
simple machine learning models.
learning model that mimics what?
A power meter.
Okay.
For instance, RAPL. So Intel has something called as RIPL, RAPL, through which it exposes what is the power consumed uh, by what they call as a package, or core or DRAM.
Interesting. So in public cloud, you don't have access to power meters. So Kepler has an ML model that mimics a power meter, so you can infer what power is consumed by a core.
By your workload. So again, at various level. So if it's your, if it's a virtual machine, which is a worker node of your Kubernetes cluster, then all these levels apply, right? So you have container, pod, VM, and node that applies to one node in Kubernetes.
Yeah. Got it.
So let's take a scenario where you have a Kubernetes cluster, and every node in that cluster is a virtual machine. When you deploy Kepler onto it, you deploy Kepler to every single node.
Does it run as a daemon set?
It's a daemon set, yes. It can be a single daemon set or multiple, but let's simplify it to one daemon set.
Okay.
So, and then now the daemon set, now Kepler runs as a process on the host, and is now able to look at the CPU usage of every process.
Each node is a VM.
Yeah.
Kepler runs as a daemon set.
Yeah.
Actually, I'm going to put it on the right. Kepler. Okay.
Mhm. And it monitors the CPU usage of every single process running in a node,
Okay.
and understands that these processes can be part of a container,
Okay.
and container is part of could be a part of a pod,
Mm-hmm.
and uh, and expose the power consumed by a pod, a container, and the node to as metrics for Prometheus to scrape.
Kepler monitors every process, understands whether the process is part of larger constructs, larger abstractions.
Yeah.
Is part IE pod VM, and then it exports metrics to Prometheus.
Yes. And to help with that, we have these models, machine learning models, that's part of Kepler. Now, I'll go a bit deeper into that. So a single model will not work for every CPU out there.
I'm drawing different things on each. I'm just kidding.
Yeah.
Because Kepler understands that it's different on each. What's going on? 2 containers, pods. Okay,
Yeah.
so now we're going to talk about the machine learning model.
Yes.
Mm-hmm. Does the machine learning model have a name?
No, I think we just call it the models. So Kepler has a sister project, so to speak, which is called a model server. And you would run a model server, one instance of model server in your cluster. And Kepler can be configured to point to a model server. So let's deploy our model server in there.
Server. And only one instance.
Is necessary.
Yeah.
It has a database of all the models that we ship.
One instance has a database of, so there's more than one Kepler machine learning model
Yeah, there are many.
of all Kepler machine learning models. Cool.
And each of the Kepler deployed onto the nodes can query for the best model that is able to provide the power value for the underlying CPU.
Each, so not the Kepler, what do you call the daemon set Kepler? Each,
that's what we call Kepler. The other is the model server.
Okay. Each daemon set Kepler can query the model server
For a best fit model.
for best. And then what makes a model a better fit over other models? What's it looking at?
So it looks at what, so in terms of models, we have something called as features. So depending on what Kepler can find from the virtual machine, it will send that metadata to the model server. And the model server looks at the metadata, looks at, okay, we've got models which work better with this metadata for this particular CPU model. And so it does the heuristics on the metadata that's provided by Kepler to
Mm-hmm.
figure out what is the best fit. So it can be, so one is the, does it closely match the CPU? Do we have a model that closely matches the CPU and the memory? That's so again, CPU can be one, the CPU family can be other. So we
When
take
you say
various.
CPU, do you mean the size of the CPU or do you mean like the type of computer hardware that's running? What does that mean?
So every processor has a family, has a model, has. So
Okay.
if you run a command called lscpu, you would find a lot of information about the underlying CPU, and
Okay.
we
So the
use that.
hardware.
Yes, the machine spec, we can say.
Okay. The word model only is confusing because we just use the word model in the context of machine learning model. And so yeah.
Yeah.
Okay. Thanks.
Uh, and what it does is, so the model server receives the metadata from Kepler. So Kepler meaning the main
The
binary
daemon
that
set.
yeah, that probes for these values, and then sends a request to obtain the best model, and the model server responds with the right model for that uh, machine, and um, and Kepler then uses that model to estimate or to predict what the underlying power meter would have given it.
Oh.
Yeah,
And and so this uses the model to predict to do its thing based on
yeah,
the ML. Cool.
yeah,
I had I wouldn't have thought to guess that like machine learning would be a part of this. It's
yeah.
very interesting. Yeah.
Yes, it is. And one other detail is that Kepler installs a small eBPF program into the kernel.
Mm. Okay,
Uh,
hold on just a moment. I'm gonna I'm gonna get this. Uses machine learning
eBPF.
model. Actually, I'm
Mm,
back. I'm a little bit behind you.
mm,
Supplied by model server to approximate energy consumption.
yeah, to predict the energy.
Okay. Okay, so basically, Kepler's on there, and we're in a cloud environment, so we don't know much about where we're running. But Kepler's on there, and they're like, oh, Kepler's like, okay, I'm going to run this program and understand what type of actual hardware I'm on. I'm going to probably do something else to understand what kind of VM I'm on. And then I can see, because I'm on daemon set on this node, I can see the processes in so therefore I could see containers, processes, pods from on my
Yeah,
own from
mhm.
eBPF maybe, yeah.
Yeah,
And
the
then
eBPF gives us the
yeah,
process time consumption. So for each process that gets scheduled, uh, it accounts for the CPU usage.
so eBPF. So this Kepler daemon set uses eBPF to do what?
Uh, to uh, to look at every single process that gets scheduled by the
Okay.
kernel, and to compute how much time it is taking, CPU time it is taking, because power consumption of a process is directly related to, it has a high correlation with the
Hmm.
CPU usage.
Uh, energy consumption. I might use SUMPTION. Has high correlation with process length,
Has high correlation with the
process
CPU.
duration.
Yeah, yeah. The process, the duration that the process is active on a CPU. So the active CPU usage. So a process can be running and then would be allotted some CPU time and then scheduled out. So we account for the actual usage uh, of each process.
Has high correlation with um, CPU process duration.
Yeah, CPU time. We call it CPU time um, as one of the metrics that
Uh,
you can find. So you can query for a process CPU time, for instance.
how long a process is active in
Yeah,
the kernel?
in yeah, let's say in active on a CPU, as in how long a process is actually utilizing the CPU.
Cool. Can you? I'm okay. I'm harping on the same thing, but I can't get over how this is different from just being cost effective and running your workloads, um, like packing your workloads efficiently and like can you tell me a time where just running your workloads in an efficient and cost effective manner without worrying about energy consumption causes more energy consumption
Uh,
than what you'd think? Yeah.
I'm not sure unless you actually
Okay.
start to measure. And so you can say that, theoretically it should be costing us less,
Uh-huh.
but this actually puts a value to
Okay.
to that. Yeah. So if you are measuring uh, the uh, the CPU usage or even the GPU usage of your process and optimizing that, then yes, in theory you are consuming less, but how less uh,
Okay.
is can only be told by again. So CPU usage is one, right? But running the same workload on different machines yield different uh, values. For instance, not every machine would have a base consumption of 300, for instance. There could
Mm-hmm.
be one which is idling at 100, for instance.
Okay.
Uh, and
And
all you need is that. So you understand that your workload requires 100 watts, and that's the actual watt usage on by your process. But uh, if you just take the entirety of the nodes usage and then attribute to the process, that's incorrect because all your workload is causing that 100 watts and sharing that idle across the others. So I'd say, yeah,
I'm
measuring the CPU and optimizing that would yield better product, better results. But we still need a way to actually quantify that in terms of watts usage. You can't declare our CPU, our workload uses, whatever CPU it is. Rather, if you can quantify it that the workload itself uses 100 watts,
mm-hmm.
that's easier to understand for anyone than
Yeah.
Yeah, so uh,
That makes sense. So
that's
being able to quantify it, and also it helps me a little bit. Your example where your host machines, some host machines might be lower, might be using less energy than others, and so then you have your scheduler that would prioritize scheduling lightweight workloads, or workloads onto that machine
mm,
because it's going to be better for the world.
yeah. And
Cool.
for each of the process, again, we split the consumption into idle and dynamic. So each process has
Mm-hmm.
two power values that it reports, which is the idle and the dynamic.
Uh-huh. Is that on the screen?
Yeah, it is.
Okay, great.
And I'm not sure if there are tools that actually calculate the idle and dynamic other
Uh-huh.
than Kepler. Um, uh, Something that is very close to Kepler in the way it works is Scaphandre. Um, but I haven't seen Scaphandre report has the concept of idle or what the dynamic is. You can get an absolute value of which is like in this case, in our first case, it'll have the 100 plus the 100. So it will report 200 in total uh,
Yeah.
against, yeah,
Uh-huh.
ours where we report it as 100, which is idle, and 100 that is dynamic. So we have a split between what the workload actually consumes versus the what is idling, what is the idle power. That's
So if you had to, like in words, what is an idle measurement? It's what the host machine, underlying
it's
host
the Yeah, let's say a simple way is that just it's total of everything, all power consumed when none of the process is actively using the CPU. So you can call it as the base power consumption uh, of a host.
when zero workloads are running.
Yeah,
It's the base. And dynamic measurement are the is the measurement of workloads,
when
plural
it is
work.
yeah,
Yeah.
when it's actively running. Uh,
The okay, not serverless. Okay. And then you said a name.
yeah, Scaphandre.
It yeah, what I can't my mind can't guess at what letters, like what that word is. Scapita?
Yeah, I can provide the link to the project. It's Scaphandre, or that's how I pronounce it. Uh, that's another tool that is able to report uh, power metrics,
Okay.
which is quite close to what Kepler does, except there is no machine learning model or concept of idle power. So relating to how Kepler is different from the other tools. Uh,
Okay. Did you send a link to me in the private chat in StreamYard?
yeah, I'm gonna do that.
If you want me to post it in the chat here, then I will. Or I could at least write the name of it on the board so I can.
Mm-mm.
I'm a visual
Yeah,
learner, so I'm trying to picture it. This is really cool. There's Yeah, this is really cool.
and the
Aha.
link.
Oh, I see why I'm having trouble understanding it. Scapenger. Uh, cool. I'm not going to write it on the board. It's enough to have it there. Awesome. So, what else do we still need to cover?
Uh, so to make the deployment and upgrade of Kepler easier for users, Kepler
Mm-hmm.
also has a small project called the Kepler Operator for
Ah,
Kubernetes.
Kepler Operator.
Yeah.
And I maybe write about that here. I
Mm.
write myself into a corner always. Kepler Operator. All right. What's Kepler Operator do?
So Kepler Operator is like any other Kubernetes operator. It
Mm-hmm.
provides a single API called Kepler,
Okay.
and creating an instance of Kepler deploys Kepler onto all nodes on your machine. So you don't, the deployment and configuration of Kepler is automated by through this operator.
Uh-huh. So you fill out, you have one manifest, apply it, and it takes care of all of it.
Yeah,
But the model server is a sub project, you said, right?
correct,
So it takes care of all the daemon set stuff.
correct. So the Kepler operator, when a user creates an instance of Kepler API,
Uh-huh.
uh, you have some spec. Let's say they create the default Kepler instance. The
Uh-huh.
default would be to deploy Kepler onto every single Linux nodes
Uh-huh.
uh, and and have the daemon set running there and report any error in if the Kepler fails to deploy for whatever reason it may be. And the other part of the operator is to upgrade. Whenever we release a new version of Kepler, the operator has the knowledge to migrate from one version to the other. So users don't have to worry about manually configuring Kepler uh, because the upgrade understands what the previous configuration is, and if there's a config change, how that would affect the newer deployment. And so the automation, the upgrade and uninstallation, installation becomes much easier that way.
Awesome.
Now,
Cool.
the operator on OpenShift, which is another flavor of Kubernetes,
Uh-huh.
which has a bit more UI and makes Kubernetes a bit more palatable to layman. Also installs dashboards, so it configures monitoring. So far, when you deploy Kepler, Kepler produces metrics, but there is no Prometheus or anything that scrapes that, right?
Uh-huh.
So the operator understands that on OpenShift there is monitoring, and it deploys dashboards, which where the users get to actually see that okay, this is the power consumed per namespace, per pod, per node, and what's the CPU architecture that Kepler detected, and all that. So that's something that the operator already provides as part of its UX.
Cool.
Uh,
Cool. So, and really, any place where you have a Prometheus solution where Prometheus is feeding metrics to a dashboard, if you already have a solution where you have Prometheus set up in a dashboard somehow, then you should be able to see all your Kepler stuff
yeah,
in there too.
yeah,
Yeah.
yeah,
Cool.
yeah.
Then awesome. And
That's
then
about
OpenShift
the
too.
entire thing.
That's it? Did we cover it?
That's everything that is Kepler, I think, in the sense that this is what everyone, people need to know about Kepler.
Uh-huh.
The other is all how Kepler works, and yeah, in short, it's just a Prometheus exporter for exposing power.
Cool. Public cloud. So, okay, so the way we're going to wrap this up is I'm going to tell you everything you just taught me, and you can
Hmm.
verify that I have it
Hmm.
correct, and we can upgrade the board in any way we might need to.
Yeah.
So, before Kepler, the problem that was happening, well, first, people weren't concerned enough about environment, about sustainability. So, I'm glad that movement's happening and people care. Um, and then the problem is that software is consuming cloud resources, but in the public cloud, you have no idea what you're using exactly. It's all abstracted away, and so the public cloud doesn't show power usage, and there's zero visibility into what wattage, what energy your workloads are consuming.
Yeah.
So then we have Kepler. Kepler is a Prometheus exporter. It exposes power related metrics at various levels. So that's process, container, pod, VM, and node levels. It
Hmm.
understands all of those. And
Right.
so with this knowledge, I was really honing in on like how is this different than just cost optimization. But you help me understand that the different hardware might use different wattage, and you can prioritize hardware that's using less wattage. But one way you can do that is you can take these Kepler metrics and you can build a scheduler that uses Kepler metrics to choose where to schedule workloads. So you're scheduling your workloads in an energy efficient way, or as energy efficient as possible, we'll say. Also, in public cloud, you don't have these access at all to you don't understand what's happening power consumption wise. And the way Kepler solves this is Kepler has a machine learning model that mimics a power meter so it can infer what power is consumed at the different levels we just talked about, the process
Yeah. Hmm.
pod. So so examples of like with numbers of how this might work is we have two machines, machine A and machine B, and each one the hosts use 300 watts. And that 300 watts is called an idle measurement. So the idle
Yeah.
measurement is the power consumed when zero workloads are running. So we have two machines, each with 300 watts. And then on this machine, we're running three workloads that are each 100 watts. So then we can see that each workload is running, is cost 200 watts to run. And here, the workload wattage is called the dynamic measurements, by the way. And
Yeah.
here, since only two workloads are running, then each workload is using 250 watts. So we can see it's less efficient because there are less workloads running over here as the
Right.
very, very simple version. But
Yeah, and one thing to note there is that we still know that the same workload is only using 100, right? So we say
uh-huh,
on one it uses 200, the other it uses 250. However,
uh-huh.
even in that 250, we know that the actual usage is 100 because that's the dynamic part that you care about,
Yeah,
uh, and the rest is idle, which is not on in your control.
yeah,
So what you can control is that 100 watts,
uh-huh,
and not the 150 in machine B.
uh-huh,
And that's where your optimization will show up. So any
uh-huh,
optimization that you do to the product, to your workload, will reduce the 100, but not the 150. So you know that if your workload is 20% more efficient, it reduces to, let's say, 80 watts,
uh-huh,
then you would only see a 20 watts reduction. But um, on the machine machine B, you would see you're still consuming 230, right?
uh-huh,
Which is not, which, if you measure, it's like less than 5% of the entire workload you were consuming earlier. So the dynamic and the idle gives you the actual uh, uh, measurement as to how much you've actually optimized or unoptimized. As in, if the consumption goes high in the dynamic, it's your workload that's creating that effect, and not the idle power. So that's where the idle versus dynamic really helps, because in both scenarios, machine A and machine B, 100 watts is what each of the dynamic power is. However, the total is different because of the underlying factors.
That makes sense. So those are the things we're looking for. So we have this 3 node cluster, these three rectangles, and we are saying that these are VMs. So we deploy Kepler onto that. So it's probably a good time to mention the Kepler Operator. So it's a Kubernetes operator. It provides a single API that automates the deployment of the daemon set and the configuration of the daemon set of Kepler. And then also when there's an upgrade, it automates the upgrade process. So it's very easy for you to stay on top of what's recent. It looks like you have something to say.
Yeah, so it deploys Kepler and model server. So everything that's under Kepler is what the operator manages. So it automates deployment of Kepler and machine and model server. So
Okay.
so let's say there's a new project that comes under Kepler, the operator would be responsible for installing and upgrading. So make it easy for a user to just install Kepler and its sub projects or whatever is needed.
Great. So it automates the deployment configuration of Kepler and model server, which we'll talk about what model server is shortly.
Yeah.
And it automates the upgrade process.
Mm-hmm.
So Kepler now, we have our 3 node cluster. This one has a pod with 1 container. This one has a pod with 2 containers. This one has 2 pods and 2 containers. And we have Kepler deployed as a daemon set. So Kepler as the daemon set is monitoring every process. It also understands if a process is part of a larger abstraction. So it understands if it's part of a container, a pod, a VM, whatever. And then it exposes metrics to Prometheus, and then it goes through your whole observability process, whatever that looks like for you.
Yeah.
I'm going to pause there. It does some more, but I'm going to jump over to the model server. The model server is deployed 1 instance in the cluster, and it has a database of all the machine learning models that Kepler has. And so each database, Kepler, this instance of Kepler can query the model server and get a best fit machine learning model for whatever's going on in their particular cluster, in their particular node. So things that might look at, there's something like if these are underscored by different hardware, it might look at the hardware usage and give you a machine learning model that's optimized for that particular hardware use.
Yeah.
So the Kepler, the daemon set, uses that machine learning model to predict energy consumption. And then it also uses eBPF to look at every process and understand how long it takes to process that process, because energy consumption has a high correlation with the compute time. So how long the process is active on the CPU is highly correlated with the energy consumption. So it uses that to get an even better picture of what energy is being used.
Yeah.
So we take this opaque idea of public cloud, we don't know what's going on, and now we're with machine learning and with eBPF and with the daemon sets Kepler, we can get visibility into the energy use.
Yep.
Is that, did we cover it? Is that everything?
Yeah, so just adding to that scenario, let's say one of the nodes there was a bare metal, then it doesn't need to ask for the a machine learning model, because Kepler can directly read off the power meter to understand what's the energy consumed. So not, yeah.
Oh, so if one was like self-hosted in a way where we do have access to the power meter. Yeah, that makes sense.
For instance, you have a KubeVirt, which is a way to deploy virtual machines using Kubernetes itself. And you may have a bare metal where these virtual machines would be deployed. and on those bare metal, which is in your control, or it's Kepler is directly installed onto that bare metal, then you would get the hypervisor level reading, which is what we call as VM level readings from the bare metal. And in so Kepler makes best effort to read off the hardware registers first, and as a fallback, would ask for a model.
That makes a lot of sense. If you have access to the power meter, no need
Yeah,
to
yeah.
guess.
You don't need to predict. Yeah.
Cool. Excellent. That's a great point. I think that's a wrap for Enlightening. Is there anything you'd like to add?
Well, thank you, Whitney, for providing the opportunity to introduce Kepler to the world.
Oh
And
yeah, it's awesome. It's such a cool technology.
I
I'm
think so.
impressed.
Yeah, and the breadth that Kepler goes through to actually bring the power values is quite a lot. So for people interested in eBPF, they can focus on that aspect. Those interested in more ML can focus on that aspect. And yeah, it's I think it's a great project to work.
Yeah, I underestimated it because I didn't know yet about how opaque it is, how you couldn't see at all. So that figuring out how that problem got solved is actually it's impressive and it's fascinating, and I'm
Yeah,
really
thanks to the
happy
researchers.
to have learned about it. So thank you so much. Oops, I'm gonna replay there we go. Thank you so much, Sunil, for joining us today. And thanks to everyone who watches the recording. And if you want to learn more about Kepler, in the description of the video is a link to the Kepler docs, which is sustainable computing. So thank you so much.